and lowering the resistance R1 and R2, we are actually going to lower the input resistance of what? Of common emitter amplifier circuit, right? We have studied only common emitter amplifier, in which we inject the input AC signal at the base, right? So we need to have base at the base. The input resistance should be higher to take more signal for amplification, right? From the power supply. So it means if we want to fulfill this requirement, we need to either increase RE or either decrease RB or both, right? So let's talk about RB. If we want to reduce it, we need to reduce R1 and R2, and by reducing R1 and R2, we are having these two constraints, right? So it means we cannot reduce this much. So here also we are having a conflicting requirements, right? So the solution would be a compromise, a trade-off. Means we can reduce it, but not much, to have low power efficiency, not much low, and have input resistance bearable to take the signal from the signal for amplification in common emitter amplifier, right? This one is only for common emitter amplifier. So the typical solution for this one is we need to select R1 and R2 so that we can have current within these two resistance in the range IE to 0.1 of IE. If we fulfill these requirement for the selection of R1 and R2, we are having a good trade-off solution having this constraint fulfilled. So with compromise and this one also. Now let's see how this thing are stabilizing our biasing, right? So we have discussed the constraint, the rule of thumb, or typical solutions. Now we will see how the RE is actually providing the stability here. So suppose emitter current increases by some reason, temperature or noise, right? Or some input fluctuations. Remember, we are not injecting AC signal. We want our Q point to be stable. It means we want our IE to be stable. If IE is stable, it means IC and other things are also stable, right? And we already make a relation of this, right? So suppose emitter current increases by some reason. What is going to happen? The voltage drop across RE will increase, and voltage drop across RE would be VE, right? If IE increase, IE multiplied by RE is VE. VE increase, right? So if VE increase, then what is going on? If base voltage is constant, and it will be constant if we have fulfilled this constraint, right? Of course, with some compromising state as discussed previously, right? So it means base voltage remains constant if set by keeping RB small. Then this fluctuation IE will only increase VE, but VB would be constant. So not now, let's see what is happening. IE increasing, because of that VE increasing, and because of that if VB is constant, VBE is decreasing. VE increase, VB constant, VBE decrease. So if VBE decrease, then we know that VBE and IC has an exponential relation. So if VBE decrease, it means IC decrease, and IC can only be decreased once IE decrease, right? So with this relation, IC decrease and IC is actually collected or drained by IE, right? So this reduce the collector and or the emitter voltage, emitter current, right? So it means we have end up with a change that is opposite to the one we have assumed, right? We have assumed that IE increase, but because of all these things once happened in this sequence, we are actually having reduced emitter current. It means this RE is stabilizing this circuit, right? So RE provides negative feedback action to stabilize IE and hence IC. This relation can also prove you, right? If we take this relation and send this IE at this side, right? We would be having 1 here. Now, if we take this VBE as VB minus VE, we know that, right? Minus VB minus VE minus sign will make this VE plus, right? So now, if IE increase, IE times RE increase, right? And this IE times this one also increase. But this one we already took very less, right? To make this constraint possible, right? So it means this will not make much different. But the thing is, we are having an increased IERE. And what is IERE? Is VE. So VE is increasing. So same VE is here, right? So if this is increasing, in the same way, this is increasing. So the ratio would be the same until this factor is small, right? Means base voltage is small. We have discussed this already, right? So RE provides negative feedback action to stabilize IE and hence IC. So for common emitter configurations or other configuration, if we take RE in the loop, we have designed our transistor with RE resistance. We are having a stable biasing because RE provides negative feedback action to stabilize IE. Negative means if IE increase, so all these steps will make it reduce, right? So negative action, right? So but later we will see that introduction of this RE in the circuit of course provide a stability in the biasing current but reduce the gain, right? And do we have any solution for that? Let's see in the later slides, right? So